5.11 practice problems. The energy distribution curve C for the Y molecules is shown in the graph above for the reaction X plus Y goes to XY. When it is done under certain experimental conditions, line A represented the most probable energy for the Y molecules, and line B represented the activation energy. Which of the following changes should be made to the graph to explain the increase in rate of reaction if the only change in experimental conditions is the addition to the catalyst? So if line B is going to be my activation energy, and I have increased the overall rate of reaction because I have introduced a catalyst, I should decrease my activation energy. So I'm going to look for something that says something along those lines. So curve C would broaden and line B would move to the left because more Y2 molecules would have the energy greater than the minimum energy required to overcome the overall activation energy. I haven't increased the overall energy of the system, so no. Line B will move to the left because a larger fraction of the Y2 molecules will have the minimum energy to overcome the activation energy barrier. Again, if I have shifted the activation energy, I've lowered it, then a larger fraction of the Y molecules will have the minimum energy. So that sounds good so far. Let's see if there's anything better. Curve C and line A will move to the right because the average energy of the Y2 molecules will increase. I didn't increase the energy of the system, so no. Line A will move to the right because the most probable energy of the Y2 molecules will increase. Again, I didn't increase the overall energy of the system. Instead, I decreased the activation energy required because I added a catalyst. Therefore, increasing the overall proportion of the Y molecules that had the required energy since I lowered the overall energy requirement. The diagram opposite illustrates how the reaction nitrogen plus hydrogen goes to ammonia occurs on the surface of ruthenium. The rate of this reaction is determined by the amount of energy required to break the bond in nitrogen. This bond is weakened when nitrogen is absorbed by ruthenium. Based off of the information, which of the following provides the best reason for the use of ruthenium in the synthesis of ammonia? So, I can see that the overall amount of energy required to break the bond of nitrogen is lowered when I am exposing it to ruthenium, so that means that I am overall decreasing the activation energy, and so ruthenium is going to act as a catalyst. So I'm going to look for an answer that most closely resembles that. It promotes the proper orientation. No, it doesn't change the overall orientation of the nitrogen at all. It provides a reaction path with lower activation energy. Again, it is acting as a catalyst, so it does lower the activation energy, so that sounds good so far, but we'll see. It forms a bond between the ruthenium and nitrogen that is stronger than the bond between nitrogen itself. No, that would decrease the amount of reaction that would move forward because that would make those molecules stickier and less likely to break apart. It decreases the frequency of collision between nitrogen and hydrogen. That would decrease the overall rate of reaction. So option choice B, providing a reaction pathway with overall lower activation energy, is the thing that makes the most sense, since it is acting as a catalyst and overall decreasing the activation energy required for the reaction to occur. The hydrolysis of sucrose is represented by the chemical equation above. This reaction is extremely slow in aqueous solution. However, when sucrose is added as shown in the diagram, the rate of reaction is about 6 million times faster. Based off of this information, which of the following best explains the large increase in the rate of hydrolysis that occurs with the addition of sucrase? Okay, so I can see that when I have added in sucrase, I am going to form an intermediary molecule that can then be broken into fructose and glucose. And so sucrase is acting as a catalyst and is overall decreasing the activation energy required. So let's see if we can find something that matches that. The reaction proceeds through a different reaction path with a lower activation energy in which sucrase-sucrose complex is formed as an intermediate. This is sounding good so far. Let's see if there's anything better. The addition of the sucrase reduces the number of effective collisions between water and sucrose that would decrease the overall rate of reaction. The reaction proceeds through a different reaction path that is independent of the temperature and concentration. That is not evident. Just because it proceeds 6 million times faster, it doesn't mean that it is without any interaction with temperature or concentration. The addition of sucrase decreases the number of sucrose molecules that have the minimum energy required to overcome the activation energy barrier. If we decrease the amount of sucrose molecules that had the overall activation energy to react properly, we would be slowing the reaction down, not speeding it up. So that one does not make any sense. So A is the only choice that has sucrase acting as a catalyst and lowering the overall activation energy by forming an intermediary. The energy diagram for the reaction X plus Y goes to Z is shown opposite. The addition of a catalyst to this reaction would cause a change in which of the indicated energy differentials. So as I am looking here, overall my energy differentials, if I add a catalyst, I am going to lower the overall activation energy, which is going to be this first hump. I would not be changing the initial energy of the X plus Y, those individual energies together, or the energy within the final complex. However, if I decrease 1, I am also going to at the same time decrease 2. So option choice D is going to be my best choice there. The equation above represents the decomposition of the compound XY. The diagram below shows 2 reaction profiles, path 1 and path 2, for the decomposition of XY. Which of the following is most likely accounts for the difference between the reaction path of 1 and reaction path 2? So reaction path 1, I can see that I have a larger activation energy present here, whereas in action path 2, I have a much smaller activation energy. If I have decreased my activation energy, most likely that means that I have introduced a catalyst to path 2. Higher temperature is not going to be represented here. We have overall potential energy and then the reaction process. And just increasing the temperature is not going to give me this clean of a differential in activation energies. So temperature is going to be eliminated. And then the catalyst being added to path 1 does not make any sense since the path 1 has a higher activation energy. So no. The role of a catalyst in a chemical reaction is to lower the activation energy and provide a pathway that is overall more favorable. So something along those lines is what we should be looking for. Decrease the amount of reactants that must be used. Nope. Lower the activation energy for the reaction. That sounds good. Let's see if there's anything that's better. Supply the activation energy required for the reaction to proceed. It does not increase the actual energy within the system, so no. Increase the amounts of products formed at equilibrium. No, it speeds up the rate of reaction. It doesn't actually force the reaction to proceed forward more than it would without the catalyst. So option choice B is going to be my best choice, and that is the only one that speaks on lowering the activation energy, which is the whole point of catalysts.